Hello everyone. Today in this video I am going to analyze this cropped cantilever beam using flexibility method. So flexibility is also we can relate as 1 by stiffness K, and so this we can say as displacement by force. So we can define the flexibility as the amount of displacement due to unit force. Okay, so if you remember, we have already discussed VFM, virtual force method. So in this method we were applying a unit virtual force and we were calculating the displacement. So if you look at with definition of flexibility, it's the amount of displacement due to unit force. So we'll be using virtual force method to analyze this using flexibility method. So how it is? So if you look at virtual force method, that can only be applied to determinate structure. And if you look at this propped cantilever beam, this is an indeterminate structure. So in order to apply this virtual force method, we are going to divide this into a primary structure, just having the loads and removing the support at D. So I removed the support at D. So now this structure is a determinate structure. I can analyze this using virtual force method. And then this is a primary structure, and we can divide this into second part, which is a secondary structure having the support, okay, this roller support at D. Okay, so we have divided this indeterminate structure into two parts. One is primary structure, another is a secondary structure, and we will be analyzing both this using virtual force method. So instead of having this roller, we are going to replace this roller with a reaction force RT. Okay. So now this, as I can say, as a primary structure which will give us a particular solution, and a secondary structure will give us a complementary solution. So now, let's first solve this first primary structure. So this is 30 kilonewton, 20 kilonewton, and the distances are 2 meter, 3 meter, 4 meter. Now when we are analyzing this using virtual force method, so if you remember, the moment diagram will be bending moment diagram will be for this. So as we don't have load for the part CD, so it will be blank, no load, so no moment. Then after that, from C will be having load. So let's increase this, and if I take a cross section here at any distance Z, so you can take Z till here, okay, from C, but it is easy for calculation or making this moment equation, so I'll take 0 Z value from the ND. Okay, so if I'm taking any cross section, so the moment at any cross section between this C and B, the moment will be 30 multiplied by, because this is the load, 30 multiplied by this distance, so this distance is Z minus 2, okay, because total is Z and this is 2 meter, so the moment at any section X will be 30 multiplied by Z minus 2. Now coming to the second part, for the AB, the moment will be, so just I'll extend this so it looks straight here, will be somewhere like this. Okay, So if I take a section here, okay, at this let me take as section YY. So the my will be, for the any section moment there, it will be 30 multiplied by z minus 2, okay, plus there is another load 20 kilonewton multiplied by this distance. Now I am considering z as from here, this is z, so plus 20 into z minus 5, okay, because this distance is 5 meter. So any section, if I am taking the moment here, it will be 30 multiplied by z minus 2 plus 20 minus 5, z 20 into z minus 5. So you can look into the virtual force method video also to understand more about this. So we have calculated the bending moment diagram, we have calculated for this cantilever. Now if you look at for virtual force method, what we do, we have to apply a unit displacement then. So because we are going to find out the reaction RT, so I am going to apply the unit display force. So unit force here is, let me take as here F is equal to 1. So due to this unit force, my bending moment diagram will be, okay, like this. So any section if I take, it will be 1 unit force multiplied by, this is Z, okay, 1 into Z, which is equal to Z, okay. So this is, I can write this was the real moment and this as the virtual moment. So the displacement at, because I want to calculate the displacement at this, at D, okay, here I am going to calculate. So displacement at D, due to this primary structure, so I will put as P, is equal to, so as we have already studied in virtual force method, it is the capital M, that is the moment due to the real beam, by EI multiplied by virtual moment due to, that means the moment due to the virtual force, virtual unit force we have applied, multiplied by dz. So I have divided this. If you look at for CD, for this part, okay, this part we don't have any moment, it will be 0 because there is no force, although we have for the unit but virtual, but it will be 0 because of the, at real beam the moment is 0. So I will start with the C, CB and BA. So if you look at, so my Z here is 0, so then Z is 2 meter, then 0 plus 2, then 2 plus 3, 5 here, then finally 5 plus 4, 9. So here the Z is value is 9. That means the distance from D. So I am going to integrate this, the second part, which is from 2 to 5. Okay, 2 to 5 I am going to integrate. So my moment is 30 multiplied by Z minus 2. Multiplied this by EI. Okay, then virtual moment is Z into dz, okay, plus then 5 to 9 meter I have to integrate. So this is my moment, 30 multiplied by Z minus 2 plus 20 into Z minus 5, okay, then virtual moment is Z, it's same, okay, Z. So this is by EI multiplied by dz, okay. So if I am going to integrate this, so 30 Z minus 60 Z, so this outside Z square, minus 60 Z by EI, this I have to integrate 2 to 5 plus 5 to 9, 30 multiplied by z minus 2. So I'll just take this out. 30 z square minus 60z plus 20z minus 100 z by EI. Okay, so here 30z square plus 20z square, so I will just remove this. So I will directly write as 50z square, then minus 60, and this is minus 100z, so this I can write as minus 160z. Okay, so this I can reduce this into so this will be 30z cube by 3. So 1 by EI I can take outside, minus 60z square by 2. This will be from 2 to 5, plus 50z cube by 3 minus 160z square by 2. This is from 5 to 9. So solving this, so first terminology it came 540 by EI plus 5586.67 by EI. So this gives 6126.67 by EI. So this is the displacement in the primary structure, okay, at D. Now we are going to find out for the secondary structure. Okay, so for this structure, the bending moment diagram will be, so at any section if I take, it will be RD multiplied by Z. Okay. Similarly, I am going to apply a unit force. Okay, so let me apply it here, unit force. So this will be displacement, the moment will be like this. So small m will be 1 multiplied by, again for z, at any distance z, it will be z, 1 multiplied by z. So the displacement at D, okay, so virtual force method, as you can see, wherever we are calculating displacement, there we have applied a unit force. So the displacement at D for this secondary structure is multiplying, so this will be multiplied for 0 to 9, because total 9 meter. So because the triangle is same, we don't have to divide one simple triangle, because here there is the triangle or the bending moment diagram was not a particular triangle, there was a triangle, then if you can divide a triangle and a square, so the moment was different for C, B and BA, that's why we have divided and we got two terms when we calculated the displacement. Here we can simply add the displacement, multiply here, so RD into Z by EI, this is for the real beam, multiplied by the virtual moment by dz. Okay, so solving this, I can just put this as negative, because here the unit force we are applying, or the RD direction, so the displacement here will be upward. Okay, but here because of the downward force, the displacement was downward, so I'll just put here negative sign because of the sign convention. So RD z square by EI, so this, if we integrate, it will become z cube by 3 EI, okay, from 0 to 9. So this gives us minus 243 RD by EI. So we have calculated the displacement for the both the primary and the secondary structure. The final step is to calculate or apply, we can say apply the compatibility condition. So if you apply compatibility condition, that means your displacement at D due to the primary structure plus displacement at D due to secondary structure is equal to 0. So the displacement was for primary structure is 6126.67 by EI, plus for secondary structure is minus 243 RT by EI is equal to 0. So this gives RT, we can calculate 6126.67 divided by 243, which gives us 25.21 kilonewton. So we got the reaction from this compatibility equation. That means we have this propped cantilever. We know the reaction here is 30, this is 20, so 2 meter, 3 meter and 4 meter, and now we have calculated this RT, which is 25.21. So from this now you can easily calculate the shear force diagram. So if I take this, so at so here 25.21 your shear force, then plus, so this is, if I take as minus 25.21 plus 30, it goes above, okay, 4.79. So I can take this as, okay, 4.79 plus 20 gives you 24.79. Okay, so this is 24.79. So this is your shear force diagram. So this, that means the reaction here will be 24.79. So you can add reaction at A plus reaction at D is equal to, it will be 50 kilonewton. So 24.21 plus 24 point, because here it is 24.79 RA. So total upward force is equal to total downward force. And we can also draw the bending moment diagram here. So this is how we can analyze our indeterminate structure using the flexibility method. So if you calculate the moment here, it will be 0. You start with this, so 25.21 multiplied by the distance 2 meter, force into distance gives you the moment. So this gives you the value of 50.42. Then after this, if you want to calculate the moment here, so it gives you 36.05. That means 25.21 multiplied by 5 meter, because I am calculating the moment here at B, subtract 30 multiplied by 3. So finally, if you are going to calculate here the moment, so it is coming 63.11 kilonewton meter. So that means moment at A is equal to 25.21 multiplied by total distance 9 meter minus 30 multiplied by 7 and minus 20 multiplied by 4, which gives 63.11. So this is your bending moment diagram. So finally we got our shear force and bending moment diagram from this analysis of the structure using flexibility method. Hope this video is useful to you. Thank you for watching.